Hello everyone. When we look around us, we see colors everywhere in sky, in a rainbow, in a flame, even in the light around us. But have you ever wondered why we see these colors in first place or what they might be telling us? Something as ordinary as a light can actually hold much more information than our eyes can see. And if light can reveal so much to us here on earth, imagine how much more it could reveal when we look beyond our planet. The light coming from stars and distant objects travels across space and eventually reaches us. Hidden within that light are clues. Clues that can tell us things we could never discover just by looking at the sky. So, how do we uncover those clues? That's where we begin cracking the code of cosmic light. Spectroscopy. The light we take for granted. What if light could tell us a story? A star is a millions or even billions of kilometers away. We can't touch it, we can't take a sample. So, how do we know what's happening there? We study its light. Every time we look at a star, we are actually receiving information that has traveled through space to reach us. What is spectroscopy? A spectroscopy is the study of light by separating it into different wavelengths. It's when white light passes through a prism and spreads into six different colors, which is known as spectrum. White light contains a range of visible colors, which is red, orange, yellow, green, blue, and violet. Different wavelengths carry different informations. How do we split a white light? A slit makes the incoming light narrow. The light reaches a prism or diffraction grating. Different wavelengths are bent or diffracted by different amounts. The colors spread apart. A detector or a camera records the resulting spectrum. This is similar to seeing a rainbow colors in a prism, but a scientific spectroscope allows us to measure and analyze them. Absorption and emission spectra. So, what exactly are these two types of spectra? An absorption spectrum happens when light passes through a cooler gas and atoms in that gas take in particular wavelengths of a light. An emission spectrum is almost the opposite. When atoms gain energy, they release specific wavelengths of light as they return to their lower energy levels. But why does this matter? Because these wavelengths aren't random. Each element interacts with light in its own unique way, producing a specific pattern. So, when astronomers observe the light from a star, they can compare these patterns with spectra measured on Earth and work out which elements are present. It's almost like identifying someone from their fingerprint, except here its fingerprint is made of light. How can light tell us a star's temperature? Hotter objects releases more energy, more blue or shorter wavelength radiation. Cooler objects release relatively more red or long wavelength radiation. But astronomers don't simply look at whether a star looks blue or red. They measure the distribution of wavelengths across its spectrum. Example: a hotter star peaks of its radiation is towards shorter wavelengths, whereas a cooler star's peak shifts towards longer wavelength. So, talking about the real life example, think about a piece of metal being heated. First, it's dull, then turns into orange, then yellow, then white, meaning as its temperature increases, its emitted light changes. Astronomers use this same physics to estimate the temperatures of the star. How can we tell if a star is moving? The universe has a Doppler effect. Objects moving towards is known as blue shift. Object moving away from us is known as red shift. Imagine a star has a particular spectral line at a known wavelength. If we observe that line, it shifted towards blue, meaning the star is moving towards us. When it shifted towards red, meaning the star is moving away from us. This is known as the Doppler effect. The Doppler effect in real life. Ambulance approaching us, meaning higher pitched siren. Ambulance moving away means lower pitched siren. The sound waves are compressed when ambulance approaches and stretched when it moves away. Light behaves similarly, but instead of hearing a change in pitch, astronomers measure a change in wavelength. Space version. Star approaching, meaning wavelengths shift shorter, meaning it's a blue shift. When stars move away, wavelengths shift longer, meaning it's a red shift. How much is it moving? Don't just say red means moving away. The amount of shift tells us how fast the object is moving along our line of sight. Simple idea. Small wavelength shift, meaning smaller radial velocity. Larger wavelength shift, meaning larger radial velocity. Scientists compare the observed spectral line with its known wavelength. A simplified relationship is radial velocity is approximately equal to speed of light into change in wavelength by original wavelength. So a tiny change in wavelength can reveal enormous cosmic motion. Spectroscopy helps us find exoplanets. This is a really cool real world application. Planet orbits a star. Then, planet's gravity slightly pulls on a star. Stars move slightly back and forth, which is leading it to its spectral lines shift. Then, astronomers measure the shifts. Possible exoplanets are detected, meaning we aren't necessarily seeing the planet directly. Instead, we are detecting the tiny movement it's causing in its star. That is called the radial velocity method. How can we build a simple spectroscope? First, we need light source, narrow slit, lens, diffraction grating, a camera or a sensor, and computer or a phone for recording. First, the light passes through the narrow slit, then the lens, then refraction grating, then to the camera or the detector, then it passes to your phone or a laptop to see the spectrum. For a demonstration, you can use a safety white light source and show how its spectrum changes when observed through the spectroscope. So, what can spectroscopy tell us? What we measure is wavelength distribution, and what we can learn from it is temperature. We measure spectral line and we learn composition. We measure line shifts and we learn motions. We measure amount of shifts and we learn radial velocity. We measure changes over time and we learn possible orbiting planets. The main message here is one beam of light can contain an incredible amount of information. From a simple rainbow to the universe, it starts from white light, then it separates into wavelengths, measures the spectrum, analyzes its pattern, then understands its stars, then it studies the planets, then finally it explores the universe. So, we don't have to travel to the stars to learn their secrets. Their light comes to us. Now, let's try the experiment in real life. So, this is a spectroscopic tube, this is a retort, this is a clamp where the spectroscopic tube is attached, and this is a bulb, and this is known as a bulb stand or a bulb base. So, Before turning off the light and seeing the spectrum, you can see a spectrum which is already present in a where there's a lot of light. Now let's turn off the light and see in the dark. So you adjust the tube according to the bulb. Here you can see a rainbow like spectrum. What I learned working on this project changed the way I look at light. Before, I mostly thought light has something that can help us see colors, but I learned that it can actually carry informations. I learned how a simple spectroscope can separate white light into its different wavelengths and how those wavelengths can be studied to understand much more than what our eyes can see. The most interesting part for me was learning about absorption and emission spectra. I realized that tiny patterns in light can help scientists identify elements and study objects that are incredibly far away. So, my biggest takeaway is that light isn't just something we see, it's something we can read. And with that, I would like to end by saying a heartful thank you to the Indian Space School for giving me this amazing opportunity to explore, learn, and look at something different, as simple as a light, in a complete new way. This project has not only taught me about spectroscopy but also made me more curious about the universe around us. I'm truly grateful for this experience and for the opportunity to share what I've learned with you all. Thank you for listening.